G'day guys, and welcome back to another Further 101 lesson. My name is Jake, and today we'll look at how to apply and interpret a log scale on the x-axis of a histogram. This video forms part of the Univariate Data sub-series, which is within the core module series on data analytics. Now, because we will be working with numerical variables, this video assumes that you already know how to draw and analyze histograms. If you are not comfortable with these concepts or you just want a refresher, please click the card above and check out our Working with Numerical Variables video before watching this one. We'll start this lesson by explaining why we scale and how to do it using logarithms. Then we will look at how to interpret an x-axis that has a log scale applied to it. We'll also explore an optional component of how logarithms and exponents are related. Whilst this is not necessary for understanding the fourth section on conversions between scaled and unscaled values, it is good to know the intuition behind a conversion. We'll finish up with a practice question to apply your knowledge. As always, to navigate each of these sections, you can use the timestamps in the video description. Now, the problem with some data sets is that they are a hassle to work with because they have a supersized range of values. Maybe the data recorded different ages of trees in a rainforest, or the profits of all companies in Victoria, both big corporates and local tuck shops. It is almost impossible to get meaningful results when this data is plotted without scaling. You'll typically end up with a very flat histogram with small frequencies in each interval and an axis that is too long to fit on the page, as we've got here. And when you try to shorten your x-axis with wider intervals, you're left with a few intervals with lots of data inside of them, whilst the rest have nothing. In either case, there's no shape to the histogram, and it's way too hard to interpret. To resolve this problem for data with an enormous range of values, we can squish the numerical data together by scaling it using a logarithm with base of 10. Remember, the Further Mathematics course will only ever ask you logarithm scaling questions with a base of 10. Therefore, the base 10 is placed as a subscript under the g of log. Now please do note that ln is known as natural log and is not the same as log with the base of 10. So please don't use ln on your CAS calculator or on your written answers. This will produce a different solution for the same data value. Back to the equation, and inside the brackets is the actual non-scaled data value. The solution to this logarithm is the scaled data value. Of course, if you want to plot a histogram, you will want to organize your data into intervals. Because the Further Mathematics subject guide only requires you to work with logs with a base of 10, you can determine your interval boundaries by substituting powers of 10 into the equation. By powers of 10, I mean the solutions to 10 to the power of some number, like 10 squared or 10 cubed. Log-scaled intervals will have a distance of 1, and hence your x-axis should be marked with intervals of 1 between each number marker. I've put the most frequently used scaled and unscaled interval boundaries into a table for quick reference. I've put a link in the video description for a PDF cheat sheet that has this very table, along with conversions instructions between scaled and unscaled data values. I'd advise you to use this or something similar in your bound reference. Let's see all this scaling in action with an example histogram. So here's some data for weights of vehicles at a construction site. We need to convert all these data values to determine what log intervals that they fall in, then tally the count of scaled data values in each interval, and finally draw the histogram. Let's try scaling the first data value to get a bit of a feel of what to do. So we have a data value of 987, and we need to turn this into a scaled data value using the logged system. So we'll take our log of base of 10, and we'll put 987 within the brackets, and using a CAS calculator we can get the solution of 2.994. Now given our intervals have a distance of 1, that means that this raw data value, when it's scaled, is part of the log interval 2 to 3. Only just, but it is in there. So if we repeat this process for all data values, and create a tally of how many data values are within each log interval, we can draw a histogram that looks something like this. Notice that the x-axis label has the word log inside of it. If you ever see this word on an axis of a histogram, you know that the x-axis has a logarithm scale applied to it. You should also write your x-axis label like this if you're drawing a histogram for log-scale data. Now you might be wondering, what the hell does a value of 2 mean? Especially if you're talking about a variable like vehicle weights. Is someone really driving a car that's only 2 kilos heavy? Luckily, this driver isn't taking a Hot Wheels car to work every day. To actually get any real meaning out of the log scale when analysing a histogram, you need to convert the scaled number back to its non-scaled raw data form. So the easiest way to do this is to just use the table that I presented earlier and I've linked in the video description. Find the x-axis marker of interest in the scaled axis marker column and then read the number inside the bracket of the related logarithm. This is your non-scaled answer. Thus, the scaled axis marker 2 represents 100 kilos. The 3 represents 1000 kilos, and so on. You can also reverse this process to find the scaled interval boundary or axis marker from the raw value. Let's try answering the question of how many vehicles were between 1000 and 10,000 kilos. So let's start with the lower boundary, 1000. We can find the row that has the logarithm with 1000 inside of it, and find its corresponding scale marker value, which is 3. We can do exactly the same for 10,000 and see that its scaled marker value is 4. Hence, the scaled version of 1000 to 10,000 kilogram interval is 3 to 4. This bar on the histogram has a count of 8 vehicles. If you're wondering why we can't just plot these raw values in place of the scaled numbers, it's because the markers on any axis must be separated by an equal distance. But the difference between each of these power of 10 raw numbers gets bigger as you move to the right. So we can't just plot 100, 1000, 10,000 and then 100,000. They don't have an equal distance between them. Whereas the scaled numbers change by 1 every single time, and so satisfy the rules of markers on an x-axis. Now, not only will you be expected to convert the axis markers, but all data values. So let's explore how we can achieve that in either direction. Before jumping into conversions, we'll look at the relationship of exponents and logarithms and their elements. If you want to go straight to the conversion instructions, use the timestamps in the description below, otherwise stick around. Take a look at this example of an exponential, a number that has an indice on it. The base number is 10, whilst the exponent or indice, which is the little number on top of the base, is 2. This indice tells you how many bases should multiply together with each other. Thus, if the power is 2, we need to multiply 2 10s together. Following the equal sign is the solution to the exponent, which is actually called the power and not the little number on top of 10. So, 10 squared equals 10 times 10, which has a solution or power of 100. If we were to write a logarithm, we put the exponent base number as a subscript after the g in log. Inside the bracket is the solution to the previous exponent. It is also the place where our unscaled data value typically goes. Notice that the solution to a logarithm is the power to an exponent. Hence, there is a link between the two. In fact, we can use the exponent equation to convert from a scaled value back to an unscaled value, whilst we can use the logarithm equation to convert from an unscaled data value to a scaled data value. Let's look at those in more detail. So there's a 3-step process to convert a raw data value to a logarithm scaled value. We'll run through these instructions with an example. The first is to actually just take your raw data value, and in this case we'll be using 1349. We'll then put this value inside the bracket of a log with a base of 10, as we've done here. Now again, If you're completing the conversion using a CAS calculator, make sure you do not use the ln button, but the log button, and put 10 for the base. ln stands for natural logarithm and will give you a different solution for the same data value than when you're using a log 10. So make sure you're using log with a base of 10. Then, using your calculator, you can find a solution. And we can see that the solution is our scaled number. In this case, we've got 3.13. So this value would fit in the interval of 3 to 4. So that last conversion from the raw data value to the log scale data value should have been fairly familiar to everyone, as we've already done it a few times throughout the video. But going from a log scale data value to the raw data value will be new. We have another 3-step process to convert in this opposite direction, and we'll run through it now with an example. The first step is to just take your log scale data value, have it ready. Now in this case, I've given you 4.3557 as your log scaled value. You could use any of the scaled values, including the axis markers. The next thing is to make this the exponent of the number 10. So we'll take our 10 and for the superscript we'll put 4.3557. The very last thing to do is just to calculate this using your calculator. The solution is your raw converted data value. And we can see here that 10 with the exponent of 4.3557 produces a solution of 22,685, which was one of the data values in our data set up the top. Now that we have an understanding of the theory, let's put our knowledge to the test. Please pause this video and have a go at each of the questions before hitting play again and checking your answers against mine. So the very first question asks, what is the skew of the data and what does that mean? So if we have a look at this, we can see that the data is probably positively skewed. Everything's sort of pushed towards the left and there's very minimal or lesser amounts towards the right. So that indicates that most of the companies in the study earn profits on the lower end of the scale, whilst a few companies earned much bigger profits. The key lesson out of this question is that you would not have determined a positively skewed data set if you had not have scaled the data using a log to the base of 10. Applying that scale allowed us to determine this positively skewed data set. So the second question asks, what percentage of companies made between $1,000 and $10,000 profit? Now the very first thing to do is check your y-axis and have a look at what the scaling is, and we can see that it's in percentage form. So we just need to add up the bars that are between $1,000 and $10,000 profit. But of course our x-axis is scaled and we don't know exactly yet which one is 1,000 and 10,000. So we need to find the scaled version of each of these values. Now the easiest thing to do is to use the table that I previously provided. But we can also apply the conversion formula to go from the raw value to the scaled data value. So let's start with 1,000. We'll put it into our log of 10 and we get the solution 3. Now we'll do exactly the same for 10,000 and we'll get the solution 4. So we need to find a percentage between the interval of 3 to 4. And we can see that that's 10% reading it off the histogram. This third question asks, what number of companies made between $100,000 and $1 million profit? Now, to calculate that is largely the same as what we did in the previous question. However, we have an additional step where we need to convert from percentage to number, because our y-axis has a frequency in terms of percentage, whereas the question wants a number of or count of companies between $100,000 and $1 million profit. But the very first thing to do is just to convert those $100,000 and $1 million values into a scaled form. So we can use the formula again and see that 100,000 becomes 5 when scaled by log with a base of 10, and 1 million becomes 6. Again, you can use these formulas or you can use the table provided before. So we can see that the 5 to 6 interval percentage is 15%, and we can read that directly off the histogram. Now the last step is to convert this percentage to a count. So we'll use our percentage to count equation, where we take the percentage from the interval of 5 to 6, divide it by 100, and multiply it by the total number of companies, which was provided earlier. And we can see that we take our 15%, divide it by 100, multiply it by 120 companies, and there are 18 companies from this data set that earn between $100,000 and $1 million profit. The last question asks, what is the modal interval? Now, the modal interval just stands for the interval with the greatest frequency inside of it, and therefore it is the interval with the highest bar. So we can directly read this off the graph and see that our modal interval is between 4 and 5. But that's not very informative. What does 4 to 5 mean? So we need to convert those axis markers, those interval boundaries, back into its normal units. So we can use our other formula for converting a log scale value back to its raw data value. So we'll take our 4 and 5, put it into the equation as the exponent to the 10. And our solution for that is our modal interval is between $10,000 and $100,000. Thank you so much, guys, for watching this video. I hope you took a few things out of it. Please don't forget to subscribe to our YouTube channel and click notifications so you can follow all of our latest updates. Also, chuck us a like on Facebook and follow notifications there as well. That's all from Further 101.